This is class 11, chapter 2, atomic structure, lecture 7. In this lecture, we continue discussion of Bohr's model. In previous lecture, we derived the equation for Rn, nth orbit radius, and this was the equation. Now we can calculate the energy of the electron of the system of nth orbit with radius r. See, this is nth orbit and this is Rn. This can be calculated again by the way we calculated this. Here this electron is experiencing the two forces, one acting outward, that is a centrifugal force, which is given by mv square upon r. This is centrifugal force. Another, this is Coulombic attraction or Coulombic force. Coulombic force, you know, that is given by F is equal to K, Q1, Q2 upon R square. Here K is 1 upon 4 pi epsilon 0, beam space 4 pi epsilon 0, and Q1, Q2, Q1 is Z, Z is the number of protons present in this, E is the charge on one proton. Therefore, it comes out to be Zd, Q1, Q2 is E, Zd into E comes out to be Zd square divided by this square of this R. Therefore, it comes out to be Rn square. And here both forces must be equal. This force acting as centripetal force should be equal to this force, centrifugal force. Let us equate these. Means the equation comes out to be mv square upon r is equal to 1 upon 4 pi epsilon 0 z square upon r square. Here this side r square, if you multiply this by r, this r is gone, and on multiplying this side with r, it comes out to be z square upon r, and v square. If we divide it by 2 or half and v square, that is equal to the kinetic energy, and we should then also divide this side also by 2. Got it? That is why we got this as the kinetic energy of the electron. We have to calculate the potential energy also, and potential energy being it a system of Coulombic attraction, it should be negative, and that is given by K, Q1, Q2 upon R. Here K is 1 upon 4 pi epsilon 0, and Q1, Q2 means Z square upon R. This is the potential energy, this is the kinetic energy of the electron in nth orbit. If we add this with this, we get the total energy of the electron, and how much that total energy comes out. Energy in nth orbit of the electron should be equal to 1 upon 4 pi epsilon 0, this kinetic energy we are adding up, z square upon 2r and this. Here sign is negative, we are adding up, therefore this sign will remain as such. This comes out to be 1 upon 4 pi epsilon 0 z square upon r. Let us simplify this equation further. Then En comes out to be, this comes out to be common 1 upon 4 pi epsilon 0. Here 2r r, therefore it would be 2r here, and this is z square minus 2z square. Let us further simplify this. En comes out to be 1 upon 4 pi epsilon 0. Here z square minus 2z square, that comes out to be minus z square upon 2r. Or we can see that En comes out to be, we can take minus sign here, minus 1 upon 4 pi epsilon 0 2r. If it's nth orbit, this is also r of the nth orbit. Here this equation comes out. In this equation, let us put the value of r in. Then this equation would be, energy in the nth orbit would be 1 upon 4 pi epsilon 0, right, z square upon 2 into, we put the value here of r, four pi epsilon 0 here n square h square, n square h square, and here it would be 4 pi square z square m. This equation comes out. Let us further simplify that. En then, here we can do that also, right? Then this is 4 pi epsilon 0, this is 4 pi epsilon 0, it would be 1 upon 4 pi epsilon 0 whole square, and this is z e square to pi square z e square m upon n square h square. Here, is that clear up to this? Let us further solve it. Let us further simplify that. Then it comes out to be En is equal to 1 upon 4 pi epsilon 0 whole square and z a square means z square e 4 z square z square. Here 2 pi square 2 pi square m upon h n square h square. Here we have got the equation for the energy of the electron in nth orbit. We know the value of 4 pi epsilon 0. We know the value of Z, atomic number of the atom, E, charge on one electron or proton. We know the value of pi, we know the mass of the electron, and here we know that of what orbit number we have to find the energy, and H is Planck's constant. H is Planck's constant. Therefore, we find this out. Now, see, this is initial, this is final. Therefore, in transition, the energy released would be the change in energy of the electron. The energy of the electron in this orbit, what is the difference? That difference is emitted out in the form of a single photon, which is equal to h nu. Therefore, we can see this is the delta E, which is equal to h nu. Suppose this is the energy of the initial orbit, and this is the energy of final orbit. Then this equation would be 4 pi epsilon 0 z e square 2 pi square n upon, only change is what? F. This is final h square, and delta E is equal to this and initial minus the final, and is final. If we subtract from initial to final, then the equation would come out to be, we can get delta E by subtracting the value of E final and E initial. So this is the equation for E final, only difference is what? That is the n, number of the n. And if we subtract this has negative sign, this negative sign, that's why it would become positive sign. And when we add these both up, the equation would become equal to 1 upon 4 pi epsilon 0 square, and here 2 pi square z square on 4 upon, we take h square and we take this out, because here it would be f minus, so there would be n f square minus 1 upon n I square. If this is for the hydrogen atom, then this becomes equal to 1, or this is gone, because value of z is 1. Here this equation comes out, and this all is constant for hydrogen atom. 4 pi epsilon 0, that is the constant. Planck's, that is also a constant. Pi constant. The charge on electron is constant, and mass of electron does not vary either. Here this is equal to delta E, and this delta E is emitted out in a single photon, means this is h nu. This is h nu. Let us further simplify that. If h goes this side, it would remain nu, and it is h cube. Nu is frequency of electromagnetic wave is equal to, you know that, c upon lambda, where lambda is the wavelength, c is the speed of the light. Therefore the equation comes out to be c upon lambda is equal to 1 upon 4 pi epsilon 0 whole square 2 pi square me4 upon h cube into 1 upon nf square minus 1 upon ni square. Here this is the equation. Let us go ahead. Here 1 upon lambda would be equal to, if it goes, c goes here, then this is left as 1 upon lambda, and we know that 1 upon lambda is nu bar, or the wave number. Therefore wave number would be equal to, here you see this, all are constant for the hydrogen atom. Therefore this can be represented as this is RH 1 upon, we can say, minus 1 upon square. This equation we get, or we can also write that the wave number is equal to, and here you get this equation that is given in your book. Its derivation is not in your syllabus. I have derived all those to make your concept clear that from where this RH has originated. This is RH, 2 pi square Me4 upon 4 pi epsilon 0 CHQ. This is a constant for hydrogen atom. And Balmer series and final is what? 2. And an initial can be any number greater than this, maybe 3 or 4 or 5 or whatever it may be. And for other series also, this number either 1 or 3 or 4 or 5 or like that, and that can be higher than this. Therefore, we can calculate through the Bohr's model the different photons emitted during different transitions of the electron in the hydrogen atom. Bohr could therefore explain the hydrogen spectrum. These are the allowed orbits: 1, N1, N2, N3, N4, 5 and so on. And when electron comes from any higher orbit to this second orbit, then that is Balmer series, and that is in visible region, from 3 to 2, from 4 to 2, from 5 to 2, from 6 to 2, or from any, say, 100 to 2, all those spectral lines lie in the Balmer series in the visible region. After that, it comes Lyman series, when N is the final orbit of the electron. An electron comes from, say, 6 to first, or second to first, or third to first. Then this is Lyman series. If it comes to second, then that is Balmer series. And if it comes to the third level from any higher level, then that is Paschen series. And this series you can memorize as L, BP, BP, H, L, BP, BP, H, L, BP, BP, H, L for Lyman, B for Balmer, P for Paschen, B for bracket, P for front, H for Humphrey. Here, when the electron from any higher orbit comes to the first orbit, then Lyman series. If it comes to the second orbit from any higher orbit, this is Balmer series. If it comes from any higher orbit to orbit number 3, then this is Paschen series. If it comes to 4, bracket series. Fun series when it comes to 5th and 6th, and so on. Therefore, in this way, Bohr could explain the emission or absorption spectrum. Emission and absorption spectrum of hydrogen atom or hydrogen-like species. Hydrogen-like species means or single electron species. For example, this is say helium. Here two protons and two neutrons. And if helium is ionized, then only one electron is left. That is why He1 positive is hydrogen-like species. Similarly, if di-positive lithium ion, that is also hydrogen-like species. There we will have to put the value of Z as 2 in He and 3 in lithium. Bohr's model could also explain the emission and absorption spectrum of helium unipositive ions and lithium dipositive ions, but it failed to explain the spectrum of multi-electron species. That's it today's lecture. We shall continue this chapter in next lecture. Till then.